Hi, Calculus. Picking up on our from average velocity to instantaneous velocity, we have our ball toss function where we've thrown this up in the air, starting at 48 feet above the ground, and it goes up for about a second, and then comes down and lands after about 3 seconds. And what we're interested in is figuring out the instantaneous velocity of this object in flight 0.8 seconds into its flight. And we've been talking about getting close to figuring that out by figuring out the average velocity from this 0.4 seconds to 0.8 seconds. So kind of close to 0.8 seconds. If we figure the average velocity between 0.4 seconds to 0.8 seconds, then we have at least some estimate of its velocity at 0.8 seconds. So notice we have this secant line, and we also have this chart where this is time 2 is 0.8 seconds, and then the height at 0.8 seconds is 63.36. And then over here we have time 1, and what we're doing is right now we're at time 1 is 0.4 seconds, and the height is 58.24 seconds. And this, we also have this calculation of velocity. So as we saw in the previous video, the average velocity on the interval 0.4 seconds to 0.8 seconds is 12.8. But what we want to do is we want to get a better approximation. So let's take our T1 and just make it closer to 0.8 seconds. So let's make it 0.7 seconds, right? And I think we'd have to zoom in to get a better look at this secant line. This is definitely a better approximation of the velocity exactly at 0.8 seconds. And we can see in the table, if time 1 is 0.7 seconds, then the average velocity between 0.7 seconds and 0.8 seconds is 8 feet per second. But we can do better than that. We can get closer yet. We can get to 0.79 seconds. We can get to 0.799. So let's just dial this up. Let's get to 0.79 seconds and zoom in a little bit more. And this is certainly a better approximation of the average velocity of the instantaneous velocity at 0.8 seconds. And it turns out that's 6.56. And if we zoomed in closer to 0.799, well, we get an even closer approximation. The problem is if we get all the way to 0.8 seconds, then our calculation of average velocity is then undefined. It breaks. But we could see what it is on the other side of 0.8 seconds. If we moved this secant line over here and we were instead of approaching 0.8 seconds from the left, what if we had the secant line over here and we were approaching 0.8 seconds from the right? Well, we could be all the way out at 1.2, zoom into 0.9, then 0.81 and 0.081, and we'd be getting very close to this 0.8 seconds. And we'd see that the average velocity on the interval between 0.801 seconds and 0.8 seconds is 6.384 feet per second. So we can see that we're approaching something between these two numbers, between 6.416 and 6.384 seconds for our average velocity. And in the next video, we're going to make this even more precise and show you how to actually calculate the instantaneous velocity. Okay, so I hope that helped, that we're approaching this secant line the length of the secant line was approaching 0, and the shorter and shorter the secant line became, the more precise was our estimate of instantaneous velocity. Our average velocity got closer and closer to being an accurate estimate of the instantaneous velocity at 0.8 seconds. Okay, I hope that helped.